Hello. In this video, I'm going to look at an integral which may require a bit of rewriting, for example. Now, here we have that this is the equation 1 over x squared plus 1 squared. Now notice that if we were to choose, like, just for the sake of looking at it, like if u is equal to x squared plus 1, what is du? Du is 2x dx, which, we see that there is no x term, right? But also, in any case, we have that, you just have a 1 up here. So the question becomes, like, how do we rewrite this without overcomplicating the integral? So the way of which that we can look at this is, what if we were to add in 0? So like if we have x squared plus 1 squared, and then let's say, for example, that we add in 0, but notice that we can do that with x squared. So plus x squared minus x squared. Okay, so what does that do? It rewrites the equation as x squared plus 1 divided by x squared plus 1 squared minus, okay, so we have minus x squared divided by x squared plus 1, and that's going to be squared. But then notice that this simplifies to 1 over x squared plus 1, and then, of course, minus x squared over x squared plus 1. Okay, so essentially we have that we can just rewrite this as the following. We have that that's going to be the integral of 1 over x squared plus 1 minus x squared over x squared plus 1. Okay, yes, that should be squared, right? So we'll have that that's going to be squared right there, and we'll put dx, right? Okay, so I know that the first one says that that's going to be arctangent, inverse of x, minus the integral of x squared divided by x squared plus 1 to the second power, and that's going to be dx. Now, once I got to this point, I know that essentially, maybe we can try to do the same thing, or how about this? Why don't we just use integration by parts for the second integral that we've just created? Because now we can have that the integral of x squared is going to be x squared divided by x squared plus 1 squared is going to be x times x over x squared plus 1 to the second power, and then that's going to be dx. Okay, now in any case, what does that mean? That means that we're going to use integration by parts, where u is equal to x, du is equal to dx. But then that means that dv is the entire x over x squared plus 1, and that's going to be squared. But how do you do that? Well, you would have to use a u substitution to find the antiderivative, right? So that would be the v is equal to negative 1/2, and that's going to be 1 over x squared plus 1, and then that would be it for our v. Okay, so now we have that essentially we can actually piece this together by continuing on with this integral, because we now know that the equation, the integral, will become negative 1/2 x over x squared plus 1. Okay, but we have that it's going to be minus v du, so that's actually going to be, let's see, because it's going to be minus v du, so it's actually going to be a plus. So we have that that's going to be plus. Okay, so let's see. So that's going to be plus v du, right? Okay, so that's going to be 1/2, and it's 1 over x squared plus 1, and that's dx. Okay. Now, of course, this is what this integral is. So just to, iterate that we are integrating this last integral, right? Using integration by parts. Now, what we do know is that, of course, this becomes negative x over 2 divided by x squared plus 1. And then that's going to be plus 1/2 arctangent inverse of x. And then it's going to be plus c, right? Okay, so what does that mean, though? That means that we've actually found what this integral is, and we can maybe box that or highlight it, whichever you prefer. So here is our integral that we found down over here. Okay, so essentially all that we need to do is take this value, or this integral, and we're going to use that's going to be, okay, so that's going to be minus that integral, so that's going to be a plus actually. So we have that when we put it all back together, we have the integral of, okay, so 1 over x squared plus 1 to the second power, and that's going to be dx, is equal to arctangent inverse of x minus, so that's going to be a plus, x over 2 times x squared plus 1. But notice this, you're subtracting 1/2 arctangent inverse of x and then plus c. Okay, but then this becomes, well, this becomes that you're subtracting this, so that's going to be positive 1/2. So positive 1/2 arctangent inverse of x plus x over 2 times x squared plus 1, and then that's going to be, plus c, right? So plus c. So we have our integral solved right here. And that was using integration by parts, right? Okay, now note that, we did solve it using where we add in 0 and then we use integration by parts, and then, yeah, we had to do some side work, right? Now, interestingly enough, though, what if I used the integral? Because most of the time a student might say, well, that looks like arctangent, right? Which it does. So yeah, 1 over x squared plus 1 dx. Now, if I was going to use integration by parts, well, how would I do that then if I use integration by parts? So in using integration by parts, I might say, well, let's say that let's get rid of the equal sign, right? For a minute. So let's say that u is equal to 1 over x squared plus 1. What is du? Du is negative 2x over x squared plus 1 to the second power, and that's going to be dx, right? Now v, what is v? V is actually just x. Why? Because dv was just dx, so we just integrate. So in this case, this tells us that we have that the integral, and we'll scroll up a little, the integral of the 1 over x squared plus 1 dx, using sort of like a integration by parts approach, that's going to be equal to x over x squared plus 1. And then what is that going to be? It's going to be plus 2. So we have plus 2. Okay, so plus 2, the integral of x squared divided by the x squared plus 1 squared, and then that's dx. Now, notice this though. Notice that in actuality though, this tells you that we can actually solve where we have that the integral of 1 over x squared plus 1, that's actually just arctangent inverse of x. And then I'm left with x over x squared plus 1 plus 2 times the integral of x squared over x squared plus 1 squared, and then that's going to be dx. But notice that what could you do with the 2? Well, what I could do probably with the 2 is just divide it out, right? So we can just take 1 over 2 and then 1 over 2. So what does that do for you though? What that does is it tells you that now you have a formula. You have a formula now for the integral of x squared over x squared plus 1 to the second power, and then that's dx equals to, so what's that going to be? It's going to be 1/2 arctangent inverse of x minus x over 2 times x squared plus 1, and then that's going to be plus c. Now, considering this though, what did we get when we rewrote the equation from earlier? The 1 over x squared plus 1 to the second power dx. We said that basically that's going to be equal to 1 over x squared plus 1. And then what did we say that it was going to be? It was going to be minus x squared over x squared plus 1 to the second power. That was just by adding in 0, remember? So that's going to be dx. Actually, let's do that. That's going to be dx. So essentially, we have that this answer tells us that we just have to say, okay, well, I know that the first integral is tangent inverse of x minus the answer that we got from the very beginning, which was negative x over 2x squared plus 1. And you could put some parentheses around there. And then that was going to be plus 1/2 arctangent inverse of x, and then it was going to be plus c. Let me just go back to verify that it is plus 1/2, and it is, yeah, plus 1/2 tangent inverse of x. So in this case though, now that I know the formula, then in that case, it's actually just giving me back the exact same thing. It's giving me back the exact same thing because once you subtract the, it's over here. Once you subtract the arctangent from the tangent inverse of x, you'll get 1/2 arctangent. So this is our answer right here, is it not? Well, in this case, we can go ahead and say that, well, we're done, aren't we? Because, yeah, we have that we derived a nice formula. So we have that that's going to be tangent inverse of x, but with a 1/2 in the front, plus x over 2 times x squared plus 1, and then that's going to be plus c. So essentially we have the answer by using a little bit of integration by parts, right? So there we just used that, we just needed integration by parts and just adding in 0, and then that was it. Now, how that might relate to how you can use that is, for example, okay, so remember that the key was that you started off with the integral of 1 over x squared plus 1 to the second power, and then that was dx, right? And we rewrote it as the integral of 1 over x squared plus 1 minus x squared over x squared plus 1 to the second power, and then that was dx, right? Okay, so now notice that if we had something like the integral of, well, suppose that we had a nice integral such as like a squared over x squared plus a squared squared, and then that was dx, right? Okay, now how would you solve this then? You would basically do the exact same thing where you would add in 0. What is 0? It's x squared minus x squared. So you have x squared plus a squared divided by x squared plus a squared squared, and then that would be minus x squared, but divided by x squared plus a squared, and that's squared, right? So that's squared, and we have that's going to be a bracket, so we could probably just put a dx at the end. But what does that do for you? That tells you that you end up with the integral of 1 over x squared plus a squared. And then what is this going to be? It's the same thing, is it not? It's just x squared over x squared plus a squared squared. Okay, but essentially that's almost like the same exact problem as it is actually, where we know that the first integral is going to be 1 over a arctangent x over a. That's a known integral. Okay, so we have that the first part is going to be 1 over a, and then we have arctangent inverse of x over a minus, but now we have an integral that we may need to work out, right? Where we have x squared plus a squared, and then it's squared, and then it's dx. Okay, so this is where we're at now. We're at the problem of similarly where we need to find what is the integral of x squared over the sum of x squared and a squared squared. That's a lot of squares, right? Okay, so here we don't really use where we add in 0 again, because that'll put you in a circle. So we'll just say, well, x times x over x squared plus a squared squared is going to be the format of which that we write this. So now we have that we can use integration by parts. Now, because I'm a big fan of the tabular method, then maybe I might just use the tabular method to do this. Okay, so we'll use the tabular method, and we'll just start off with that. Okay, well, we have plus and we have minus. Now, what we're going to do next is basically just choose, let's choose a darker color. We're going to choose our u to be x, right? And then we're going to do 1. But actually, let's go ahead and do 0, right? And let's go ahead and add in another plus sign there. That way we'll have that the x over x squared plus a squared squared, that's actually a simple u substitution where essentially you have negative 1/2 1 over x squared plus a squared. Okay. Now, from there, and you can verify this using reciprocal rule, right? Where you have negative 2x and then the 2's cancel out, but then it's positive. Okay. Now, in this case, we go ahead and we integrate again. So we have negative 1 over 2a, and then, let's see, that's going to be arctangent inverse of x over a. So now we try to put everything together, right? Where we'll just say, okay, well, sort of like tic-tac-toe. So we have that we go down here and down there and then down that way to get the plus c. Okay, so in any case, that's going to be negative x over 2 times x squared plus a squared. Consider this that it's only just, x squared plus a squared. Okay, so minus, and then we have double negatives, so it's going to be plus. So plus 1 over 2a, and then that's going to be arctangent inverse of x over a. and it's plus c now. Okay, but what did this represent? This actually just represented the integral of x squared over, let me write it over here. It's x squared over x squared plus a squared squared, and then it's going to be dx. So this actually is equivalent to that. Okay. But it doesn't solve our original question, does it? Because our original question was a squared. Okay, so our original question was a squared over x squared plus a squared squared dx. And the way of which that we did it was we said that the first integral, when we wrote it as x squared plus a squared over the denominator squared, is going to be 1 over a, and that's going to be arctangent inverse of x over a. But then we said that it subtracted this integral that, we can go ahead and box or circle. So we have that it was that integral, right? But we figured it out. It's going to be minus, so we have that it's going to be minus the x over negative x over 2 times x squared plus a squared, and we extend it so that we can have the plus 1 over 2a arctangent inverse of x over a. Okay, now I'm out of room, but we know that basically you can put another set of parentheses in either case. So let's go ahead and move this so that you can see it. So now I'm going to go ahead and just say, well, what do we do here then? Okay, so from here we have that this is going to be equivalent to 2 over 2 times 1. So that's actually going to be 1 over 2a. And let's actually just do this where we just write it neatly. Actually, there's no reason that we should be right here, because we can just say it right there. So like equals to, okay, so 1 over 2a arctangent inverse of x over a, but then you have that it's going to be plus 2. Okay, so that's going to be plus, well, not 2, but yeah, it's divided by 2. So x over 2 times x squared plus a squared, and then we have that that's going to be plus c, right? So what I'm saying is that the general formula is this right here. Okay, so we have that this is the general formula in either case. Now, whether or not you said that you wanted to divide this whole thing by, let's say, a squared, then in that case, that would technically change the formula, where you'd be saying that the integral of 1 over x squared plus a squared squared is equal to 1 over 2a cubed arctangent inverse of x over a plus, okay, so you divide by a squared, so that's going to be x divided by 2a squared times x squared plus a squared, and then just plus c. So that means that I can actually check my work then, because now I have the most generic formula where a just has to not be equal to 0 in either case. Because what do we do here? We're going to go ahead and just say, well, okay, the integral of 1 over x squared plus a squared, not a squared, but 1 squared, is equal to, accordingly, and we'll put a dx there, that way you can say that I didn't integrate properly. So that's going to be 1 over 2 arctangent inverse of x plus x over 2 x squared plus 1, and then that's plus c. Okay. Now, in either case, we can essentially check our work, like by differentiating, right? We can say that, okay, well, if I was to differentiate 1/2 arctangent inverse of x plus x over 2 times x squared plus 1 squared plus c, that this should equal to, the integrand function. But we really don't need to, because we found it, if we scroll back up, we found it right here, right? Yeah. So this is our answer. 1/2 arctangent inverse of x plus x over 2 x squared plus 1 plus c. So, we'll go ahead and go back, and we'll see that, well, this is the exact same thing, actually. And, actually, this formula that I have just derived by the use of integration by parts, I mean, we can actually use it entirely for anything else if we wanted to in actuality, right? Um, but, the only thing, though, is that if we do this, that we have a formula for this particular integral, then what does that mean, like if I had a different integral, such as like, like let's say that, for instance, sorry about the colors, say for example you had y equals to x over x squared plus 1 squared, and you wanted to look at this from x from 0 to 1, and let's say that you wanted to find the volume that's rotated about the y-axis, then you know that pretty much that if you want to find the volume, well, in any case, if you're integrating from 0 to 1 or looking at it from 0 to 1, then we can just use the shell method from 0 to 1, and then we'd say 2 pi x times the height of the equation, which in this case would be just x, divided by x squared plus 1 squared, and this is going to be dx. Then see like how this gives us 2 pi times the integral from 0 to 1 of x squared over x squared plus 1 squared, and then that's going to be dx. Okay, so in any case, for example, like, how does this help us? Well, remember that basically we did find a formula for the general form, did we not? So, if we go back over here, I think that basically what needs to happen is that we have to basically, kind of like reuse where we have the integral, right? We have the integral of a squared over x squared plus a squared squared. Okay, so let me see if I can copy this, actually. Okay, so we have the integral, and oops. Okay, so we have this integral, and we have that if we rewrite it just by multiplying by a squared, then we can kind of generalize it, if you will, like like where you have a squared over x squared plus a squared squared, and that's going to be dx equals to 1 over 2 a arctangent inverse of x over a plus x over 2 times x squared plus a squared plus c, well, I think that what I'm trying to say is that if we were going to, say for example, rewrite the equation in the following manner, where we say that a squared over x squared plus a squared squared is the same thing as 1 over x squared 1 over x squared plus a squared, and then it's going to be minus x squared over x squared plus 1 squared. So what I'm saying is that essentially we already know the answer if we integrate on both sides. We already know the answer for this one right here. So in either case, like, you know, we have that if you want to come up with a general formula for the x squared over x squared plus a squared squared, then really you just need to use the exact same formula that you just found in either case. Like, you found this one. So that's something that I'm going to leave, you know, that for you to figure out, that when you rewrite the integral, how we just, you know, kind of added in 0, it's kind of interesting that, you know, you can basically kind of go, in a way, it's kind of like a circle, sort of, right? But we did find the formula in either case, like earlier for x squared over x squared plus 1 squared, but I'm trying to actually generalize it. So in this case, we have that it's going to be the integral of a squared. Actually, here's how I'm viewing it. I'm just moving this on that side and that on that side. So I have 1 over x squared plus a squared dx minus the integral of a squared over x squared plus a squared squared, and then that would be it. So what I'm leaving you with is to go ahead and just plug in the generic formula into the last integral over here, like this one right here. And we know that that's just arctangent, right? Okay, so with that being said, you should be able to derive the formula very easily in either case, of which you're going to notice that there are some similarities in either case with the formulas, because essentially the only difference is a sign, essentially, right here. Like, you have that either it's a plus or a minus. And then, you know, that's actually kind of cool when you think about it, because then in that sense, all that you would need to do for that integral that we just looked at, you know, like the shell method where you had x squared over x squared plus 1 squared, that's going to be equal to the integral of 1 over x squared plus 1 dx minus the integral of 1 over x squared plus 1 squared, and then that's going to be dx. But again, we have formulas for all of these, actually. We have formulas for 1 over x squared plus 1, and then now we have a formula that is for 1 over x squared plus 1 squared, meaning that it's really just a plug-and-play situation, even if you do put the 0 and 1 and the 2 pi, the 0 and the 1, and then you put the 2 pi, and then, you know, well, you know, you would have to put like the 2 pi, right? We'll put the 2 pi there, and 0 to 1, and then just add, and then that would be it. So I'd like you to essentially try to find the volume of that where we use the shell method for that very interesting integral that I began with, which was over here, right? And in any case, if you want to just rewind back to where you found the integral of 1 over x squared plus 1 squared, then, you know, you're just really substituting and evaluating from 0 to 1, multiplying by 2 pi, and similarly, you're just using arctangent as well. But if you go ahead and you figure out this one too, where you get the general formula for x squared over x squared plus a squared squared dx, then in that case, that's actually going to be pretty useful as it relates to integrals of which look at like this in this form, or even integrals that look like this in this form, because you may be misled to believe that, oh, I can't really use integration by parts, or maybe like in the future you're like, I can do partial fraction decomposition, and you'll find out that you're just going in circles actually in terms of finding the solution. So that being said, the method really depends on the function itself, which in this case I believe that the most convenient way to do this is by the use of integration by parts, or tabular method by the use of adding in 0.